Line integrals is like one of the most important topics of this class. So partial derivatives, vector fields, all of this we're leading you for line integrals and some couple of theorems we're gonna cover next week. Line integrals is amazing. We're gonna do something really cool. We're gonna integrate a function over a curve. We never done this before. So we integrate it over lines and like, okay, from here to here, area below the graph, that kind of stuff, flat surfaces. Integration means collecting heights. So in my calculus 1 class, I show people the COVID cases, the big cases in January 2020, then February, blah, blah, blah. So when I want to know how many total people got sick, I'm actually integrating this area. It gives me all the heights add up together. Integration is a fancy summation. It comes from the sigma notation anyways. But what we always did till now, we always found we integrate over the lines. But that's not correct. What if we want to see the paths and add things together over a curve? So try to draw this. The idea is area of a curved surface. In 2D, we don't have a curved surface because 2D is 2D. But in 3D, that area that we had before, I will come back. This area, it's a fence, right? This looks like a fence. What if it's actually tilted? That is a big deal. We never learn how to do that because it's hard. It requires calculus 3 knowledge. So engineers, civil engineers, and physics majors, this is very important for your job. What if we're integrating over this? Then we're still finding heights, and we're still approximating them with lots of rectangles. But it can be done easier, and it has a deep meaning also behind it. And so see it as a fence. I see it as a fence. That's, I think it's easier to imagine, the fence. Line integrals. Did you finish drawing? Then let me show you something cool. This is how it might look like. The fence. So what if the domain is a line and I have a 3D object floating in space? For example, it's a roof. And I want to know only what's the area below, above this curve. I'm finding the projection of this curve on this 3D picture. Everything is curved, everything is 3D, and then I'm finding this area. That's one of the applications. And the best visualization is, I think this one. Yeah. Okay, figure 6. This is a hike. I'm hiking from A to B. Here it is. But because it's color-coded, maybe you're guessing that hike is not flat. Okay, for two-dimensional creature, it is flat. But for us, it's not. It's a damn mountain. So your hike now doesn't have slope 0. It's not flat. How to find that? That's a line integral. Isn't it cool? When the moment we go to 3D, even moving from one place to another place is not simple anymore. In 2D, everything looks flat. In 3D, it might have elevation and curvature front and back. That's where the line integral comes into the picture. Here it is 2D. I'm going from A to B for two-dimensional creature. That's easy. I find arc lengths. No, in 3D, it has heights. And that's how I see a fence, right? Like, it's a fence. So we're stretching it. This is how it looks when you stretch it. And then you see that sometimes you will go up, sometimes you will go down. And then you find that integral. Sometimes it will be negative and sometimes it will be positive. That's the best. And there's a formula, of course. The best representation I found, I really liked it. The goal, write down, given a curve C, the C is the one on the floor, and the function f, that's the one in the space, three-dimensional object, or function. Find the area of the fence under f over C. So f and blue is C. We have three-dimensional object. We choose C. C cuts through the three-dimensional object and creates F. Both are curves, right? And now we find this area. We still can approximate it with rectangles. So that is why, it's going to be an integral, blah, blah, blah. What is this area? Let me make it better. What is this area? Question mark. So the formula is, we'll have several formulas, so get ready. Definition. This formula is stupid. But we have to show you it first. But like this is very unusual when you don't give you like a nice formal looking thing first. But that's how explanation is working. Integral over c of f x y ds. Every time you see ds, that means we're doing the line integral. Equals line integral of f over c. That's notation. So every time you see ds at the end, that's a line integral. Line integral of f over c. F is the function inside. C is the function we're integrating off or on the domain, basically. So f will go inside of the integral. C will be integration, limits of integration. Guess what? We will have, let's see what it is. I don't remember. Oh, nice explanation here. Line integrals, curves, blah, blah, blah. Oh, this will be helpful. I explain in a second why. Arc lengths will be involved. Did you notice? So like if I want to find how long this thing is, we're going to do arc lengths, right? And we'll learn arc lengths like 3 or 4 formulas. There was the integral, derivative squared plus derivative squared, and so on. Depends on the formula. So we're definitely going to have some arc lengths involved. And that's a huge square root. It's exactly the formula. Write it down. F over C, integral of F over C. F is, as always, whatever is inside is in 3D. We're integrating over 2D. ds is at the end. ds is a notation for the line integral. How to do that? It will be integral from a to b. F. And now we're going to have to find the parameterization. Write down in terms of t. That's what we're doing here. That's going to be parameterization. Times a huge square root dt. That's arc length. A square root of derivative squared plus derivative squared. That was at the very end of calculus 2. But we also reviewed in this class. This is the formula. Is this too messy or you got it? Or should I erase my notes? Do you get it? Integral of f. ds will be integral of f. So it's still f, but we just need to rewrite it in terms of t. Times the square root. And that's the arc length formula. Derivative squared plus derivative squared. Make sense? Not really, but we're going to do examples. You can also notice that this part in blue is actually the same as the magnitude, right? What is the magnitude? A huge square root, derivative squared plus derivative squared. Oh, the magnitude is a huge square root, stuff squared plus stuff squared. So if we're taking derivative squared plus derivative squared, it's the magnitude of the derivative vector. Yeah. Magnitude of the derivative vector. So that's one way people remember sometimes. It's a magnitude of the derivative vector. I like remembering as the arc length because it makes sense. We integrating over C. This is C. Well, to integrate over C, we need to find lengths of C. That involves arc lengths. Arc length formula is this huge square root, so that makes sense to me, right? And also, this is ds at the end. That's the one that gives you this domain thing. The integrating over what? Over the line. Line has the arc length. Don't have to write this down, but it's nice to know how do we derive ds. Just like in calculus 2, we introduced a line. We wanted to ask its length. Well, if it's a snake, you cannot really take it and make it flat. It will bite you. So why not just to approximate it with some arcs, segments. Then each segment creates a right triangle. ds equals ds squared equals dy squared plus dx squared, blah, blah, blah. Those kind of things. Everything comes from Pythagorean theorem. That's why it's so impressive. So some applications, you will see it in your homework. Write down. Integral of f over c. It should have ds at the end, but sometimes people just don't write it down. Is the area of the fence below f over c. So that's what I told you. F is in 3D. C is in 2D on the floor. So what is going to be that fence area? That's a line integral. Well, in my case, I did not really do it well, like so. You will see in the homework, they will ask you to find density or mass. So if we give you density, I always mention density of your lungs, right? Your lungs have an unusual density, or liver, actually. Liver has pretty cool unusual density, and it's different at the edges and then in the middle, blah, blah, blah. Then how heavy is your liver? Well, actually, line integral will give you the mass of what? Of C. Like imagine this thing on the floor is the wire. So that's pretty cool too. How heavy is the wire if we know the density of F? Then the integral gives you the mass of C. And if you don't put anything inside, so it's 1, then it just gives you the length of C, literally arc length formula. So if there's nothing inside, there's no height. No height, right? Or like no height. If there's no height, it gives you the length of the snake on the floor, and that's arc length. Does that make sense? I'm starting talking like a smoking pirate. Very annoying. Parameterization. We're almost done. Let's do something from your homework and explain to you how to do it. I will do this example next time. I think I have a video on that one. Oh, no, that's we already have. Pythagorean theorem. Some kind of ideas of tricks. I don't like to call them tricks. Here's the formula. It's the same thing. F times the arc length. What I want to show you is example. So you can start doing your homework. Find integral x squared plus y squared plus z squared ds over c. Okay, so this object inside is a 3D object. Actually, it's 4D object. You have 3 units as input and 4 is the output, 4-dimensional. Over C, we have to give you C, where C is helix. So it's going to be a pretty cool example. C is a helix. We will ask you to create parameterization. In this case, it's a classical one, so I will tell you what it is. But you will see in your homework some examples how to create parameterization from that. Solution. What I find confusing for students is to read where is what. So small f, so the whole formula is usually looking like this. Integral over c f ds. So now we can write down what we have. Given small f is written in terms of x, y, and z. And it is x squared plus y squared plus z squared. That's a 4-dimensional object. X, y, and z is the input, and the output is the 4th dimension. Now, the formula tells me, let's go back to formula, that I need to rewrite this in terms of t. Okay. And I need to figure out A and B. Okay, that's also weird. So let's do that. Maybe knowing parameterization of the helix will help me. So did they ever tell us from where to where? Oh, they did. Where helix with, yeah, that's given. So put comma with t running from 0 to 6 pi. Okay, so we have t given. F is given. t is from 0 to 6 pi. That will go into integral from 0 to 6 pi. Nice. Because at the end of the formula is dt, if you can see. So we're integrating with respect to t. The only thing missing is we need to get rid of x, y, and z and rewrite it in terms of t. So we're trying to figure out this formula. You have to build parameterization. Step 1, write down what is given. Step 2, find parameterization. Either we give it to you or you have to figure it by yourself. In your homework, you will see classical parameterization of parabolas and lines, which we can do on Thursday if you want. I can help you with that. Helix has known parameterization. Do you know what helix is? I mentioned before, but maybe you don't remember. It's a spiral. Helix also, you can imagine a DNA. This is exactly what DNA looks like. From the top, it's a circle. If you look from the top, you will see circle on the floor, right? But actually, the spiral never goes back to the same place. So it keeps spiraling forever. But because in 2D, it has a shadow of a perfect circle, that's when you can guess that x and y in 2D will be a circle. X of t and y of t will be r cosine t and r sine t with some radius, and we don't know radius. It can be big and can be small. Maybe it doesn't matter. We will see right now. Maybe it will cancel out somehow nicely. But then this is in 2D. What is happening with z? Z. I will give you a hint. Yeah?
Can you explain why we did the 6 pi?
Oh, that's given.
Okay.
So given f and given from 0 to 6 pi. Yeah. Put the comma here. C is helix with t running from 0 to 6 pi. That's given. Or else we don't know how far to go on the helix. So x and y creates a circle in 2D. But in 3Ds keep growing up and down. Hint, remember cylinders. What is a z variable for cylinder? Z. But I want to get rid of z, but I still want to go up and down forever. What is it going to be? T. Do you all agree? So when t is large, we're going very high up. If t is small, we go very high down. That's the idea. Yes. Not small, large negative. Yeah?
How do you know the slope of the helix? Why is it not like 2t or 3t?
Good point. In this case, we're going to do the classical one. Very smart question. Why it's not tilted also and so on. Yeah, this one is a classical one. So we have that. Step 3. Rewrite f. F can be changed now in terms of t. That's the goal. X squared plus y squared plus z squared gives you r squared cosine squared plus r squared sine squared plus t squared, which nicely simplifies to r squared plus t squared. Do you need help to figure out why we simplify it like so? We factor out r squared, and we got sine squared plus cosine squared. So we wrote f. Finally, write down the integral. Integral over c. F. Now f depends on t. That's what we wanted. Let's first not do that. F was depending on x, y, and z. And ds. ds, that's notation for the line integral, has a formula. We figure out it's going to be in terms of dt. T is from 0 to pi over 6. So on the helix, we're going to stop at some point. That's the idea. From 0 to pi over 6. That was not pi over 6. 6 pi. That was given. F now is written in terms of t. And we simplified it. So it becomes r squared plus t squared. ds has a formula. Remember, it's a huge square root. Huge square root of what? That's the interesting point. I remember it's a huge square root. I remember there's a dt. Derivative squared plus derivative squared. Right? Derivative of what? Do you remember? Or at least tell me. So that's the confusing part for students. The formula tells me x prime squared plus y prime squared. Some formula even tells me it is r. Magnitude, where is it? Here it is. Magnitude of r prime. Interesting. What is my r? That's the confusing part. It's going to be very important for this homework specifically. Where is r? This is r. X, y, and z in terms of t is r. So I'm going to move it to the left. I'm going to write down that this is what r of t looks like. It's a vector. And it consists of r cosine t, r sine t, and t. So when you build this parameterization, you're building a vector r. And the formula has lengths of r prime. That's part of the formula. Or the square root of derivative squared plus derivative squared plus derivative squared. Let's find the derivatives. Integral from 0 to 6 pi, r squared plus t squared. Blue color, huge square root. Derivative squared. What's going to be the first term? Do you know what to differentiate? Do you know what's going on? Do you know what class is that? Do you know what day is it today? If you can answer any of these questions, you did fine. Better than some people. So we're differentiating this. R cosine t gives you minus r sine t. With minus doesn't matter, it's going to get squared anyways. Sine t squared plus derivative squared plus derivative squared plus derivative squared plus derivative squared. If you have 5-dimensional r, you will differentiate all of them and square all of them and add together. R sine t gives you r cosine t squared, and the last derivative gives you what? 1 squared. Thank you. dt. Told you it's going to be huge. So what is the square root actually gives you? Square root of, do you know? If you simplify, r squared sine squared plus r squared cosine squared gives you r squared, right?
Where did the 1 squared come from?
Oh, derivative of this t squared.
Oh.
So if you want, let me write down. R prime is minus r sine t, r cosine t, and 1. And that's what we're plugging here. I usually don't write extra notes. I just differentiate right away because I'm finding a magnitude of the derivative. Derivative squared plus derivative squared plus derivative squared. So what is the answer for the simplification?
2r squared.
How did you get 2r squared plus 1? How did you get... Well, let me ask other people.
Actually, just be r squared.
We cannot just change like that. Let me ask other people now. Well, of course you can. I don't mind. Did anyone calculate? R squared factored out. Sine squared plus cosine squared gives you 1. So it's going to be r squared plus 1, right? Agree? Good. Finally, let's just integrate. People like, when can we just finish this? Yes, we can. It's going to be square root of r squared plus 1 of integral 0 to 6 pi r squared plus t squared. Why did I take it out? Can I do that? I don't know. Looks sketchy. Because it's a constant. dt has nothing to do to r. R is a constant. It's the radius of the helix. It's how big the spiral is. 2 units big, 4 units big, 100. So you just integrate this integral. R is a constant, t is a variable, and you integrate it t cubed over 3, right? So it's not too bad. R squared plus 1. R squared times t, 6 pi minus 0 gives you 6 pi, plus t cubed over 3 gives you 6 pi cubed over 3. You can check. I think I'm correct. Like so. What do you think about that? That's only first part of line integrals. We're gonna do some crazy stuff on Thursday. Very interesting stuff, though. Very cool stuff. Basically, when you're running, sometimes when I scoot home and the wind is strong, if the wind is behind me, pushing me, then I'm scooting faster. If the wind is towards my face, it slows me down. We're gonna finally calculate how to figure out that. What is the whole total charge of the wind, magnetic field, and so on? That is crucial, very important. So that's gonna be very interesting on Thursday. Good job, people. Have a good day. Don't get sick.